for social media analytics. I primarily work on our data provider layer, interacting with Instagram APIs or DataSift or any of the other social media providers. We do think our topic matchers, for example, typically do about 200 to 300 a second per node. So we've had up to 50 nodes at a time. So we get a lot of data flowing through at once. I really enjoy distributed systems. I started out by helping a professor write a threading library in Java, which, as we all know, threading is the funnest thing in computer science, right? Because nothing ever goes wrong there. I finally got pretty sick of it and said, crap, how can I do concurrency in a way that makes sense? And this professor, he wrote some software in Erlang, just playing around, that ended up being used by Cisco for simulating their network cards, and it was much more performant than what they had before. And so he said, well, Cody, if you're interested in this in concurrency, you might think of it as a form of distributed system. And so he guided me to Erlang, where concurrency is done in a very distributed style. Each of the processes has their own memory space, their own heap, their own stack. You send messages between them just like you send messages between nodes on the network. And so for me, I started getting into distributed systems from the concurrency field. So distributed systems, we deal with a lot of different kinds of problems. There's the problem of how do I make these things available? You know, the idea of replication in case something goes down. On the flip side, we think, how do I make this data consistent across all these replicas? And those two opposing forces, we always strive to find the right balance between them. Well, Paxos is an algorithm that leans on the consistency side. In fact, its whole point is to have consistent data across your cluster. The original paper for it was written in a very odd style that left most people going, what? It was written as an allegory. So picture in your head a Greek parliament from thousands of years ago. And these members of parliament might sometimes be in, they might sometimes be out. On certain issues, they may care and want to actually cast their vote on things. Others just say, hey, let me know what you guys decide, because I really don't care about this particular issue too much. And so Leslie Lamport, he's kind of a big deal in distributed systems. He wrote a lot of papers. He was eventually awarded a Turing Award. And one of his key contributions was the realization that a really abstract concept, well, the fun thing of deterministic finite state machines. So let's say you've got several nodes in your cluster. If they are deterministic finite state machines, then given the same messages in the same order, they will all come to the same internal state. Well, you know, most people say finite state machines, that's just that theoretical stuff you learn in school. There's not really any practical applications for this. Well, you know, just every database that tries to maintain any kind of consistency. So before we get started on learning about Paxos, which is a way of using these concepts to maintain consistency across your cluster, let's start with a bit of an object lesson, we'll call it. So 1, 2, 1, 2, 1. You guys can be 2 together. 1 and 2. All right, so that ends up perfect. 1s stay here, 2s come with me.
What was I?
You were not counted. You're going to help me in the middle.
Okay. All right. Great.
You don't count.
I don't count.
I'll be right back and I'll explain the rules to you guys in just a minute. Sure,
Okay. let's subvert the whole system.
Yeah, so I'm guessing that because they are getting their instructions private, they're going to be.
Well, maybe we'll get instructions in private too. I actually have no idea what he's doing. But nice day. Yeah. Yeah. Well, great. They're across the street, so it's real easy to do those guys. Yeah. I was going to do Zupas, but I was too late. Oh, that's what you're missing out on. Huh?
What would you do?
I don't know, sandwiches. Yeah, I don't know. That's the weird thing, I guess, about Zupas is it's like, do you get like a bunch of salad and soup too, or like, yeah.
Yeah, we can get a bunch of different kinds of sandwiches, a big thing of salad, not berry salad.
Oh, nice.
Super yummy.
It's nuts about berries.
Like caramelized.
Is your office right by Mulligan's?
Yeah.
Yeah. Okay. Golf course. Yeah, right. That's why I was asking. Yeah, there's a Zupas right there. Yep. Well, they really went far away, huh? This is quite a network partition.
Oh, zero.
Yeah.
Drop the mic.
Yeah. Yeah. It's like, now what I haven't told those other people is I'm done talking. And so you can all go home and we'll just see how long it takes. What should we cover next month? You guys, how many people are you going to have in so typically what we do is we alternate between like a paper reading month and like a practical, here's a way to use things month. Would you guys want to present storage?
Yeah, sure. What date?
It's the 3rd. Oh, let me see. It would be August 16th. And if you want to advertise or something too, then we can probably draw more people than the 20 typical regulars that we get. I assume you guys have a pretty good network of advertising.
All right.
Better than I do. Better than I do. Yeah.
So, welcome, Grand Legion of Rome. You and another legion on the other side of Carthage are invading their city. But the problem is, if you don't invade at the same time, you're not going to win the battle. I mean, it's going to take both of you to beat Carthage. Luckily, you can send messengers over to coordinate, try to figure out a time to attack. But just keep in mind that if the Carthaginians capture messengers, well, it may not be easy for them. So some of them might escape to help with dwindling numbers over time. But the idea is coordinate with the team over there, using only messengers that you send. And if one of you attacks without the other, you lose. And that's the game. Any questions?
Okay, so we're just doing Byzantine generals?
Yep.
Yeah. Okay.
No problem.
Okay, great. So we have to coordinate the time and place?
Just the time.
Just the time.
Single
so
value.
Just pick a time, and then we're going to decide whether or not to attack.
Also, is there any difference between trading costs?
Nope, we're going to keep this simple. This is strictly a consensus problem.
All right.
Best of luck.
All right. Well, so I guess we need to send messages. Okay. So let's say 3 o'clock. Should I just go over and say 3 o'clock? I'm going to go over and say 3 o'clock. And then what? Do I come back? I guess I don't know if I'm allowed to come back. Then I'm going to go over and say 3 o'clock, and they should send a message back confirming. And then we'll just see if Cody's going to like kill people or what's happening, like with these messengers.
Yeah.
Really, what we're going to do is we're going to see how long it goes before Cody's timeout fires.
Yeah.
Yeah.
So,
Okay.
Pretty sure go and say 3 o'clock, and if you don't come back, we'll just attack at 3 o'clock.
How about, tell you what, unconditionally, you guys attack at 3 o'clock, regardless of, like, if they send back another message, like, no, 4. Yeah, okay. Okay. Yeah, just go at 3, always, just no matter what. Okay, great. And then if I don't come back, so keep sending messengers until 3 o'clock. But just say 3 unconditionally, we're doing 3.
Yeah.
Pick one.
I'm guessing 3 a.m. That's up to that number.
Oh, you just put them in timeout. Busted. All right, 3 o'clock.
There I go.
Didn't go so well.
I think we broke it.
One of us got through.
Didn't we break the? That's the thing, is if you don't have a Byzantine generals problem if everyone is just like psycho, right? Like if everyone is just like pre-committed to something, like you can't make a decision. Really, what we should do is we should have been explained the rules. Well, I don't know how to. Actually, I don't know what I'm talking about. Just ignore me. You guys should all just ignore me. I'm the Byzantine general here that's ruining everything. This is going to make for a really good recorded video.
Hey, it's 3 o'clock. Are you guys attacking or no? Yes.
Yes.
Yes. All right, we all got lucky.
Yeah.
That unconditionally modifier was not part of this.
We win. Right.
Good job. You guys took over Carthage.
Sorry, I ruined the thing.
All right, so if they hadn't said unconditionally, would you guys still have attacked the 3 group that just came in?
No. I would have been pretty good.
And you think about that, because
I never heard back from us, so.
right. I mean, so how do you solve that? How do you guarantee that you guys are going to attack at the same time? Well, unfortunately, networks aren't so kind. It has nothing to do with being caught. You can't sneak through a router. How do you guarantee it? You can't. There's no 100%. You have to specify a point at which you can accept the risk of failure. Maybe, what if none of your messages had got through? JT, what if I hadn't let you through that first time and you didn't deliver that unconditionally?
If you had continued to drop packets and none of the people got through, then we would have lost.
Mm-hmm. You would have run out of soldiers. So this is kind of an issue. You simply have to tolerate a certain amount of risk when you're dealing with a consistent distributed system. So the consensus problem, it's the basis for a lot of different things. Leader election. How do we decide which computer in this cluster is in charge? The atomic commit, which is the one we'll primarily be focusing on tonight. JP, what other things can you think of from that are built on top of the distributed consensus problem?
I don't. I'm not good on my feet.
Okay, I apologize. Well, basically, there's a whole bunch of different things. It's kind of the basis of a lot of problems that you find in distributed. So let's say you have transactions. Going back to that distributed finite state machine idea, where if every single one of these gets the same messages in the same order, then they're going to be in the same state, right? So we get transaction A, transaction B, transaction C. As long as every single state machine gets every single message in the same order, they're good. Easy peasy, right? Well, up until you start losing processors or network latency, or hey, because networks are networks, or these things come in different orders because networking. Or hey, packet loss, that's another fun one, right? So what guarantees do we need? First, we want some safety properties to make sure that we don't munge up the state so badly that we're in irreparable harm. So the first one is, of these things that come through this stream of messages, only things in that stream can be chosen. So let's say we are a distributed database. We're getting messages coming in. We don't want to say, oh, you're depositing $25 into the bank account. Well, we're going to deposit 32 because why not? Well, that's not a good property. Only proposed values can be chosen. At most, one value can be chosen at a time. In other words, if we get a deposit and the withdrawal message as a bank, at the same time, half of our cluster should not get the deposit if the other half is getting the withdrawal, at least in that order. Does that make sense? Are there any questions? Okay. For liveness, to make sure that, we're not just spinning our wheels for the next eternity selecting a value, if a value is proposed, a value will eventually be chosen. Eventually, no guarantee as to how long, because it's kind of the nature of distributed systems. But hey, if you combine that with this, you've got decent guarantee. So 4 things a node in this cluster can do. It can propose a value. It can vote for, or rather, if there are multiple transactions coming in at the same time, which transaction do we do first? We can propose a transaction. We can vote for one of these. We can accept one of these, or we say, all right, we've voted. We've got a clear winner. This is what it means to accept, to commit. And we can learn a value that has been chosen. So here's our system. 4 replicas. One of them is in charge. We're not going to worry about how it's in charge, but it is. All right? So our bank starts off, our account starts off with a balance of 0. When we get a deposit of $25, wow, this animation is going super slow. Okay, so the one in charge, there are a few phases in Paxos. There's a prepare phase, and this is the one that we're in right now. The one in charge says, hey, I have gotten a request to deposit money into your account you would like to value. So I'm going to send it out to all the replicas. They receive it. So you see each of these replicas has, they say width, back up, sorry. So the one in charge, it is saying, I've received a request to deposit $25. It makes a prepare request. So this is the first message that gets sent out. See the number 1? That is because it is tagged with the number 1 value. If it is the third time it has tried something, it will probably be number 3 or something bigger. The idea is it is monotonically increasing. This number only ever gets larger. Each replica says, I have seen nothing yet. When I have seen 1, I will store that I have seen 1. When I see 72, I will put 72 here. If a preparation message comes in that is smaller than or equal to the number that I have already seen, I will reject it, because that means it is behind the time. So it sends out this preparation message, says, hey, I've got a value. This is attempt number 1. I'm not going to tell you what the value is because there's no point yet if you're going to reject it. And they'll say, hey, we haven't seen anything yet. So yeah, we'll accept it. No problem, not an issue. So they return an ACK saying, yeah, we accept number 1. Each one of them accepts it. So now the replica says, well, first of all, the replica has gotten a quorum to acknowledge. That was over half of the voting nodes. So it says, all right, we'll move on to the second step. So now, this is an accept request, not a prepare. It is for number 1, the one that they have promised that they're not going to accept a number less than. And it says the value that they're going to do. This is the transaction itself. It sends that out to all of them, lets them know. If this number is larger than this number, they're going to say, nope, sorry, someone else has proposed something, and try again. Just try again. Start over from phase 1. Otherwise, they're going to accept. And in this case, they do, because it's the one that they promised that they would accept. So it says, great. So these 3 nodes know that they have individually accepted it. What they don't know is that everyone else has accepted it. Additionally, there are probably other nodes in this cluster who aren't voting. They're just let me know what you guys have decided. Because the more nodes you have voting, the more messages you're sending, the more network bandwidth you're using, the more likely there is to be some kind of failure happening. So as long as the quorum of the voting nodes have accepted, it will let them know, and they will all let all these other learning nodes who aren't voting what the state is. Easy peasy. What could go wrong? What kind of failures can happen?
A lack of a quorum.
Yes. Exactly. What happens if less than half of them, or what happens if over half of them crash? Well, there's a paper, the SLP impossibility result, which says in an asynchronous system, where you're sending asynchronous messages, and 2, these nodes can take as long as they want to accomplish. You cannot guarantee consistency. It is impossible in the face of one processor crashing. And so what this means is we cannot allow our system to be fully asynchronous. We cannot give them unlimited time. We have to eventually set a timeout. If we haven't gotten it within 5 seconds, 30 seconds, 2 hours, whatever your business use case is, we have to set a limit at which we say, well, you're down. Or, if we want to get more complex, we have failure detectors and all sorts of other things, but still the same kind of thing. But that is the general gist of Paxos. It is very fault tolerant. In the event that less than half of the voting nodes have accepted, or have crashed, excuse me. In the event that less than half of them have crashed, if over half of them are correct, it will eventually choose a value. Now, another complication that can happen, what if there are multiple leaders? That can take a while to sort out. And I invite you to go and read up in Wikipedia and other places how that can be handled. But that's generally the gist of Paxos. Are there any questions?
Yeah.
Okay. If you wait long enough, someone will ask.
Well, can we work through some examples of how things get handled?
Sure.
Are retries part of the protocol, or is that something you can decide at a different layer?
Yes, you can. What you do is the leader says, well, we've timed out, or I have gotten rejection messages. So I can either try another value, something else that's on this queue and try again later, or I can just try again right now. I have to increase that number that the message is tagged with because this is a new proposal. Yes.
Okay, so on the notification of the accept, this thing here, what happens if the node on the right was fully participating in this exchange all the way up until this point? So it got promised the accept message originally came and said, yeah, I can accept that, reply, that it was going to accept it, and it never got the notification from the leader that, okay, this is what everybody agreed to accept. So what does it do then?
At this point, its state will be slightly different than everything else. However, because of there are lots of different ways you can do this. You might have some kind of heartbeat thing going out with events saying, hey, we've accepted these things. Perhaps it becomes a learner node. Perhaps, like it's right here, I swear. Well, again, it also goes back to the true general problem where you don't have the perfect, you cannot have perfect consistency. There is a certain degree of risk. But any future transactions are going to require the participation of the other part of the quorum. And by definition, if you're going to have a full quorum, then I have to draw this. Do we have a
Yeah, there's
whiteboard?
the whiteboard's behind you,
Okay.
and there's markers right there.
Great. So we
Maybe
have- let's say
use
we
a
have-
darker color.
Pardon?
I'll get you a dark.
Oh yeah, a dark one. Brown. Let's say we have 5 nodes in our cluster. 2, 3, 4, 5. Here is one possible form. Here is another possible form. Here is another possible form. No matter how you do it, in order for a transaction to pass, at least one node that, no matter which part that makes quorum, there will be at least one node that is in both sets of quorum. And it can help with the rejection or it can say, no, this isn't right, this transaction can't pass. So I don't have a perfect answer. I haven't used this in practice. I've simply read up on the theory, so I apologize if I can't.
Well, I understand. I just.
You're asking if a node misses?
The node on the leader node on the one in the middle and the one on the left, they would accept. And so now they believe there's $20,000 responsible to this other one. Instead that he was going, it was going to accept, but didn't ever get the notification that, well, okay, we decided to accept. So is it assumed that everyone accepted it anyway because of what they said they were going to do?
Typically. Again, I apologize. I have not worked on this problem in a professional setting or anything, so I can't give perfectly concrete answers. Some things that I've read have said that there is a rollback method. Paxos is, if you read the Google Chubby paper, which uses Paxos, they say the theory behind this is very well understood, but it's a non-trivial problem, and there's lots of different use cases like this where it's application dependent. Maybe for your implementation of it, you have to send out a rollback method. Maybe there's something going on. I'm seeing a lot of weird looks.
The power went out.
The keynote's over. So. So there's a lot of things that are going to be application specific or specific to your business.
The internet works.
Does Paxos ever make any suggestions or suggestions about how to lead?
It can be used as a leader election. By virtue of accepting a proposal from one of the nodes, you are accepting it as a leader.
Now, it seems as though you have to have some kind of concept of how many nodes are in the network. Is that the case?
No, that is correct.
Okay.
So it's generally considered a static configuration. If there is an addition or subtraction, it needs to, all the nodes need to be notified of that, or at least the leader node needs to be notified of that so it can maintain a count of, okay, what is quorum in?
But I understand that you got another interesting issue where you've got to maintain state across all of the leaders.
Again, going back to that two generals problem, that's why we started with this. It is not possible to have perfect guaranteed consistency in a distributed system. You simply accept a certain amount of risk that there might be some inconsistencies in there. Therefore, even high consistency systems can introduce inconsistencies.
Oh, did your laptop go off? Is that what happened?
Possibly.
One of the things about Paxos that's interesting is the only way to find out a value that was learned is to run the protocol. You make a proposal with a null value. So if for some reason your node is behind and missed a value, you can run you can propose a null value that says, I'm not actually going to set this value, but I just want to see what the quorum thinks. And the quorum can respond and say, we already picked something. So if you had a node that was missing a value, that's how it would find out. Typically, so there's single decree Paxos in the sense that this is just choosing a value. Typically, you want to choose a log, right, of values. And so your values that you're choosing, you basically run multiple instances of this Paxos protocol across your log. So you have log element 0, log element 1, log element 2. To choose the value for log element 2, you may decide that you've heard about log element 1, 0, and 3, so you need to go figure out what 2 is. So you can run the protocol to go figure out what 2 is, so you can make progress, if that makes sense.
And that's what I meant when I said the heartbeat.
Yeah. Yeah. It can just every so often, on a clock, run the protocol, propose a value essentially, and find out that one has already been chosen.
So basically, if your server, say a server cluster 3 goes down, so they're shut down and then they eventually restart on the property. They would just send out that null provoke.
Yeah, they'd say so let's say in this depiction that we had on the TV of the proposal, The only node that actually knows that a proposal has been committed is the one proposing it. The other three nodes don't know that they've finalized what the balance is until they run their own proposal. If that makes sense. So it's sort of weird in the sense that there's a little bit of asymmetry between the nodes. The one that's making the proposal is the only one in the position to find out all the other nodes agree on this value.
Oh, that was an aspect of it that I missed.
Yeah.
So still on that. Isn't it send the proposal with the same proposal number that it thinks they already had, or even send a new proposal with an incremental proposal number?
You'd send like the 0 proposal number. You say, I'm proposing the 0 value. And then everyone is going to come back and say, no, we're already on proposal number 7. So that's where we are. It's 7, here's the value. And you go, oh, okay, great. Yeah. Yeah.
When you get rejected, it tells you.
Yes.
It tells you, no, we already accepted this proposal and this is the value.
Yeah. Yep.
Right, that part of it.
So if you think of it as a typical list, and these transactions are happening one at a time, and what they are choosing is which is the next transaction. And in the case of this one, that state is somewhere on the cluster that they run the proposal to find out what it is on that particular one. And from there, they can build their internal state from that stream of events.
Interestingly, Wikipedia has a bunch of like ASCII art of like all the different possible. Like I haven't usually seen a lot of ASCII art on Wikipedia, but
Yep, and it shows. I didn't show the learner nodes on here. I didn't showcase what happens, how it works in the event of certain failures. There's a lot of literature out there about how to do this. It's one of the most studied protocols in the field. So strongly recommend you go and read up more on it. Leslie Lamport wrote a follow-up paper called Paxos Made Simple, which describes a variant of Paxos called multi-Paxos. The Paxos is actually a whole family of subtly different algorithms. Some can accept Byzantine failures, some can accept multiple leaders, there's just a whole wide variety of it. So what we covered here is just the basic Paxos that is then modified to suit different needs.
On that note, I'm curious what the presented result of this proposal addressing the but what did he say the result was? What did he prove
That the algorithm is correct.
not correctly doing what? What did it give you theoretically? What are the assumptions that have to be proved in order for the result? And the distributed systems proofs are always
Right.
very context specific.
Right.
Say, oh, so he proved this. Well, what was the context in which that result was proved?
All right, so those are the assumptions. Well, I could look it up here in front of you, but I cannot answer that question. Not in the any kind of satisfactory manner.
When we say that a database is strongly,
Yes,
aren't we saying that it's using this protocol?
not
no.
necessarily.
So typically a database doesn't have multiple computers that it's running on.
Right.
So-
You say distributed database.
Sure, a distributed database that's
Or
ACID
a
compliant would have to be
Right.
using some sort of consensus. Yeah.
There's RAF, there's this, there's several out there.
So
Matthew, that is something that we've learned from, what's the guy that does the blog post about
Paper.
paper?
Yeah.
Mhm.
Kyle Kingsbury.
If there's one thing we've learned from him, and a lot of distributed databases are not consistent.
Yeah, it
Yep,
turns
very
out,
true.
there's bugs.
So basically, the CAP theorem, it was a conjecture proposed by Eric Brewer, which said there are 3 desirable properties of a distributed database: consistency, availability, and partition tolerance. It is not possible to have all 3. This was partially proven true later. by saying that in the event of network partitions, you must sacrifice at least one of either consistency or availability.
Many people sacrifice both.
Yes, that is generally the default thing. And so a lot of databases that say, oh, we're strongly consistent, actually aren't. And if you go to APHYR, he goes through and looks at all these different databases and queuing systems that claim certain consistency guarantees and says, BS. In this condition, you're not doing it.
He wrote this system called Jepson, named after Carly Rae Jepsen from Call Me Maybe, because the database will call him Maybe. Yeah. So another interesting sort of point that I think helps with understanding why this protocol would work, and this is kind of maybe a subtle detail, is when a proposer starts, it might have a value in mind, but what it's going to do is it's going to send out its proposals to the other replicas in the network. And the other replicas are going to reply with, either I've rejected your proposal because I have a higher proposal number, or I'm accepting your proposal because it's the highest proposal number I've seen so far. But then it can send multiple things back, and it can say, I have never seen a proposal before, or I have actually already accepted a lower proposal number already. In the case that a node that is replying already accepted a lower proposal value, the proposer's value switches. Whatever the proposer was thinking it was going to switch, it must propose the value that the other node had already previously accepted. So now the node who's proposing becomes a driver for getting the previous value accepted. So that's sort of a subtle detail, but what that means is if there's races between two proposers, if you have dueling proposers, that way they converge on the same value. And so because of that, you end up getting all sorts of interesting, sort of side effects, in the sense that you have a database, you have a leader that ends up trying to lead an election on a value that it wasn't even trying to set. But as long as all of the replicas are behaving in this manner, then you end up getting the overall desired behavior of that everything converges to one value.
So eventually a proposed value.
Yes, right.
In that case, if your network is partitioned in half, if one node overlapping, then you've got two leaders trying to propose two different values, they'll both converge.
Yes. Yeah. That ends up, that property of choosing whatever previous accepted value, the highest proposed previous accepted value you've seen, solves that problem of, as long as there's just one node, the majority will end up picking the same thing. Yeah. So.
Like I said, I suggest you go and look up the leader election things, because there's lots of nuance to that I wouldn't be able to have time to go into there.
Yeah, it's interesting. So he proposed Paxos. Leslie Lamport wrote Paxos while attempting to prove that it was impossible. He didn't believe general consensus was possible, and so he wrote Paxos as a result of his proof to try and prove, like, as he was proving that it was impossible, he was like, oh, well, actually this works.
Proof of contradiction.
So that was sort of an interesting side effect, but yeah, he did not believe that it was a possible thing to do. So he wrote Single Decree Paxos, the Paxos paper you mentioned, which is like a part-time parliament is the name of the original paper on the island of Paxos. And then sort of the literature and in conferences, the opinion of everybody was Paxos was way too complicated. And in fact, they told him after his first publication, or after his first attempt to get it published, they said, you got to take out all this Greek stuff. This is making it way harder than it needs to be. And sort of, he didn't like that suggestion, and so he just kind of left. Paxos actually stayed unpublished for 2 or 3 years, and he just left it in the filing cabinet because he didn't want to rewrite it to take the Greek stuff out.
Thankfully, he eventually wrote Paxos.
Yeah, so eventually he did end up getting it published. The opinion of the industry, of academia, was it was still way too complicated, and so there was a lot of feedback, like Paxos is this ridiculously hard thing. And Leslie Lamport has just been like going deaf, or going, what's the word when you can't, hoarse. Thank you. Leslie Lamport's been going hoarse over decades trying to convince everyone that Paxos is actually really simple, you guys. Geez, it's really simple.
It's more complicated than a 2-phase commit, but less complicated than a commonly used 3-phase commit.
So he's been trying really hard to get everyone to agree that it's simple, but over time, like all these papers keep coming out saying, like, okay, so Google made a paper called Paxos Made Live, which is like, I think that's their paper. Well, there's a bunch of different Paxos papers. Google wrote a paper where it was their engineering experiences trying to get Paxos to actually work. And the reason why is because Leslie Lamport talks about single decree Paxos for this value, like I said. He leaves the figuring out how to extend it to a log as an exercise to the reader. There's all sorts of practical issues about what happens to get the log to come back, how to have a log saved to disk, how to persist in the case of shutdown. You know, all these sorts of problems are not detailed in the Paxos papers. And so there's all these like engineering papers about here's how you can figure out how to get the multi-decree Paxos, which is not actually, everyone has their own flavor of multi-decree Paxos because there isn't actually a specific suggestion written down anywhere by Leslie Lamport anyway. So there's Paxos Made Live, Paxos Made Simple is Leslie Lamport's paper. Then there's Paxos Made Moderately Complex by a different group that's trying to figure out how to implement Paxos. There's all sorts of different Paxos papers coming out where people are saying, okay, actually it's really hard. Okay, actually these are some corner cases and details that are really hard to get useful in an actual engineering system. So if you've heard of Raft is a paper where one of their main goals for their consensus algorithm, which is slightly different than Paxos, is understandability. And about half of their paper is actually their data about their ability to teach the Raft algorithm versus the Paxos algorithm to groups of students, which is kind of an interesting thing to see in a distributed systems protocol paper, all this data about how easy it is to learn. So anyway, the Raft paper is titled In Search of an Understandable Consensus Algorithm or something like that. But anyway, yeah, but Paxos is sort of like there's a few other consensus algorithms. There's Atomic Broadcast. Zookeeper basically has its own consensus algorithm that works pretty well. View stamped replication. For some reason, for some reason, no one really seems to, like, it's like Paxos is the one that everyone knows. I don't know why people don't know about view stamped replication, but now everyone knows about Raft because, geez, you go and look at the Raft website, they have like 90 different implementations of Raft now. There's like 5 of Paxos. So anyway, there's my short tale of the history of Paxos.
That's what I got. Thanks for coming and have fun. Eat pizza.